Okay, before we go on, I'd like to just make a historical point about the technique we were just introduced to in the last video called completing the square. It comes to us from Persia, from this guy, in about the middle of the middle of the 9th century A.D. This is his name in Arabic. This is the Arabic transliterated into Roman script. I can't pronounce that, and I can barely pronounce the name that he's more well known by, Qarathimi. The Z, I'm told, and the M translate to sort of a THM sound in English. In any case, in the 9th century, he wrote a very famous book. Here's the title in Arabic. Here's the Arabic transliterated into Roman script. You'll notice the words al-gabar. This is where the word algebra comes from. And the title of the book can be translated as the Compendious Book on Calculations by Completion and Balancing. And the word al-gabar is translated as completion or reuniting. I understand that Qarathimi had to actually make up a word because the word in Arabic at the time was referring to the reuniting of a bone. So the next time that you're frustrated because you're studying algebra, you can blame it on the fact that you're studying the legacy of al-Qarathimi. Anyway, let's go back to some examples of how to complete the square. Alright, let's practice completing the square. Remember that the formula, or the idea, the strategy, is to reduce the left-hand side of our quadratic equation to a perfect trinomial square, so that it looks like this: x squared plus bx plus something equals the right-hand side. Alright? The right-hand side is all the stuff that we had to move to the right-hand side, so the left-hand side looks like this. Now, we have to put something in here to complete the square, but before we do that, let's notice that the leading coefficient here is 1. And it must be a 1. Otherwise, this is not going to work. So, when you are manipulating the quadratic, make sure that you manipulate it in such a way that the leading coefficient for x squared is 1. Now, b, of course, can be anything. All right, b can be any real number. Actually, it could be a complex number, but we're not going to deal with complex numbers in this case, in this course. So it can be any real number. And what we do to complete the square is we add b over 2 squared to the left-hand side. If we add it to the left-hand side, well, we have to add it to the right-hand side as well. Okay, so let's practice that a little. Suppose we've done our manipulation and we have x squared plus 10x on the left-hand side and some other stuff, usually just a coefficient or number or constant on the right-hand side. So what do we put in here? Well, it's going to be plus something. Well, b equals 10. That means that b over 2 is going to equal 10 over 2, which means b over 2 squared is going to equal 10 over 2 squared, which equals 5 squared, which equals 25. So I take that 25 and I plug it in here. And now I have created a perfect trinomial square. In other words, I have created this is the same as this, x plus 5 squared. Let's test that to make sure it's true. Now, x plus 5 squared is the same as x plus 5 times x plus 5. So we know how to FOIL this, right? X plus times x is x squared. X times plus 5 is plus 5x. Plus 5 times x is plus 5x. And 5 times 5 is plus 25. Combine like terms, and I have x squared plus 10x plus 25. Okay, and also remember, the 25 has to go over here as well. Otherwise, the equation's no longer going to be equal. And of course, now we know that this, this, and this are all the same. All right, let's do another one. Suppose I have x squared plus 11x plus something equals my right-hand side. All right, well, it's the same idea. b equals 11. So b over 2 is going to equal 11 over 2. Oh, darn, I cannot reduce that. That's the fraction in its simplest terms. I cannot reduce that to an integer. Oh, well, I have to deal with a fraction. I have to deal with a fraction. I can do that. All right, so b over 2 squared is going to equal 11 over 2, the entire quantity squared. If I square a fraction, that's the same as squaring numerator and squaring the denominator. We know that from prior experience. And 11 squared is 121, and 2 squared is 4. So we plug in 121 over 4 on the left-hand side. And of course, I have to add that to the right-hand side as well. Let's do another one. Let's do a negative number. Let's see what happens then. So now I've reduced my left-hand side to x squared minus, 12x. And I've got some constant over here on the right-hand side. So what do I put in here? Well, it's going to be a plus again. And now b equals minus 12. Well, it's a negative number, but I can deal with negative numbers. b over 2 is now going to be minus 12 over 2, which is minus 6. b over 2 squared is going to equal minus 6 squared, which is 36. So I put a 36 here, and I have to add 36 to the right-hand side just to keep the equation balanced. Remember, the book that Karahimi wrote was Completion and Balance. Okay, prove that's true. That's true. Okay, so now this is going to equal the quantity x, and I plug in this guy, which is now minus, so it's minus 6 squared. And we can check that as well. X minus 6 times x minus 6. X times x is, that is the same as that. So it's true. Let's do another one. Suppose I have x squared minus 13x, and that's equal to something on the right-hand side. I don't really care. Well, I'm going to do this in my head. This is going to be plus 13 over 2 squared. Right? And of course, I'm going to put that over here. 13 over 2 squared. Alright, what's 13 squared? Oh, that's 169. So, this is going to be x squared minus 13x plus 169 over 4 equals the right-hand side plus 169 over 4. And that's going to equal x minus 13 halves squared. And we're done. We've completed the square. That, of course, is going to equal whatever I have left on the right-hand side, plus 169 over 4. And that's completing the square. It's fairly straightforward. All right, in the next video, we're going to solve some equations, some quadratic equations using completing the square.